Fella asked why light bends, essentially. He asked me this question about 2 weeks ago. I gave him a rain check, and I got to answer his questions, okay? And I thought it was a good question. He says, why a beam of light enters a medium and refracts? What determines the angle in which the light bends? You know, like it goes into a prism, and suddenly you see that sharp bending, and then bends again when, you know, goes out the other surface, right? And he says, what determines the specific path of where the light signals end up? And I think a lot of you have seen, you know, the prisms and light going through there. You can look it up on the internet. You'll find tons of pictures of that and videos, etc. Right? If the light signals just propagate through random paths and doesn't pick a direction, then the whole medium would light up. In other words, you know, if you take a light bulb, light goes in every direction. And so he's saying, why does that light go like in a directed path? Why doesn't it refract and disperse, you know, sideways and go all over the prism, for example, right? And so that's the question we're going to try to answer today, okay? However, in real life, the light beam always travels one path after entering the medium, okay? So he wants to know why that pencil sharp, you know, pencil beam, ray, I guess you could call it, why it goes completely straight. That's the question. And also related to that is, does light bend? Does light curve? Primarily curve, you know. Bend like sharply, yeah, we can say it bends, whatever that happened there, right? We got to explain that. But does it curve like, you know, in a nuanced way, little by little? Is that what light does? It curves? And then the other issue we need to answer, which is the main subject today, does light go through walls? Can you see through walls? Like if I put a flashlight on the other side of your wall, can you see? I mean, I'm talking about a real wall, like made out of bricks, right? Can you see through the bricks, the flashlight on the other side, or a candle, or whatever you want to put there? That's the question we have to try to answer today, okay? See if we can. Okay, and essentially he's talking about this prism, right? You've seen that. You have this white light coming in from the left, goes through the prism, and it kind of breaks up in all these colors, typically 7, right? And then it comes out of the other side also as a bunch of colors. Okay, and the question of what happened there, you know, how did we break up light in all these colors, and why is it bending? You know, why does it bend? Okay, that's part of the question. And again, I think right there we more or less get the idea that light does go through solid matter. I mean, a prism is solid, but it's translucent, you know, so you can see more or less through a prism, not completely. It's not a perfect glass, right? But you can see on the other side, and light does seem to be able to go through solid things. Okay, that's the issue. Okay, but what's one of the problems with this? One of the problems is the speed and the outgoing speed. The light is coming in at 300,000 kilometers per second. We're just going to assume that this is done in the vacuum, okay? Or air is very close to vacuum as far as what is known as a refractive index. But let's just assume it's a vacuum. You're in the vacuum. You're out there in space. You're going to shine the light. Okay, it's going to go in there 300,000 kilometers per second, right? And it's going to hit this wall, slanted wall of the prism, right? And here it is. Here's a picture of it so that you can see it. The question is, it comes in as white light at 300,000 kilometers per second. And then the question is, you know, they say, well, when it hits the prism, its light slows down. Okay, light slows down. That's their explanation. They say light travels slower. And as you can see, it breaks into different colors because they have different wavelengths. Okay, but the bottom line is they say light slows down because it hit a brick wall. Essentially, that's what it is. And what's happening, according to them, the mathematicians, right, is that the atoms inside the prism are absorbing the light and re-emitting the light. Okay? And they do so probably from atom to atom or from atom to the space there on the right-hand side, right? Whatever the case, they're saying that atoms are absorbing and then re-emitting the light that they receive, the white light. And so they have these different wavelengths for each one, and that forces the beam to bend. Then it bends again once it reaches the other edge. The problem here is that now light has to go fast again because it goes back into outer space, right? And so the question is it traveling fast or slow when it comes out on the other side, on the right side of that prism? And so that's one of the questions we need to answer as well, right? The speed of light. What makes the light go fast again? I mean, if it slows down inside the prism, how does it pick up speed afterwards? Okay, that's the question, right? Okay, and so here we have another explanation from the R2D2 or the AI, right? The bots. And it said when light passes from a denser medium to a less dense medium, it speeds up. Why? Because it encounters fewer interactions with the medium's particles. In other words, they're saying that inside the prism, the atoms it's a denser material. It's solid, it's denser, and so we can imagine, you're going with your car and suddenly you hit a brick wall, right? Or you travel through some kind of, haystack maybe, right? And you go through the haystack. While you're going through the haystack, you're going to go slower, right? But then when you come out the other side, well, your speed should continue normally, right? That's essentially what they're saying here. It says, well, light travels at a constant speed in a vacuum of 300,000 kilometers per second, right? It slows down when passing through a medium due to interactions with the medium's atoms. In other words, there you see a piece of glass maybe, prism, you see it sideways, no problem. It goes into the prism, goes slower, right? Once it exits the denser medium and enters a less dense medium, these interactions decrease and the light speed increases. But they haven't explained why it increases. I mean, and here, let me show you what I'm talking about. Now, I'm going to illustrate it for you so that you understand the question. The question is the question. What is the question? Here it is. Here's a car. Okay, I'm going to run this. You're going to see a car going through water. You're going to see, in fact, two cars. The first car is going to go in there, go slower, and then continue at the speed it was going through, right? It was coming through. It was coming at 60 miles per hour, goes maybe to 40 miles per hour, then continues at 60 miles per hour. The second, I think it's a truck, goes in there, and it's stopped altogether at some point. And then it has to restart and move on. And so the question is, how do you explain that for light, assuming it comes to a complete stop? Can light come to a complete stop and then start again all of a sudden at the same speed, 300,000 kilometers per second in a vacuum? It'll go from 0 to 300,000? How? How did it do that? That's kind of a magic trick. So here it is. Watch this. Here's the two cars. Now the next truck is going to get stuck. But this one stops. And then it cranks again. And only then does it leave, okay? So what happens if we replace the car and the truck with light? I mean, light slows down, goes through a medium, then continues at its regular speed because it doesn't encounter as many atoms. Is that the reason? Or is it because, it cranked the motor up again? And how about if light comes in there and stops altogether? Now you have to restart the motor, right? And just in case, I want to make sure people understand that the mathematicians have proven evidence, verified, completely proven. They have the evidence that they stopped light altogether. Zero motion of light. And the first one was done, I think, 1999. The second one was now, they tried several times, but they tried again in 2015 or 16. Here it is. Okay. And so quantum computing scientists stop light in a cloud of atoms. And they say a cloud of atoms seen here as the red glow in the middle of the images was used to make the stationary light. And in 1999, a team at Harvard University successfully slowed a beam of light to a crawl. Then in 2001, they achieved the seemingly impossible, completely stopping a light pulse. This was done by manipulating light within an extremely cold cloud of atoms. Okay, so they froze the atoms, and by doing so, they froze light. Then they were able to restart the light, essentially releasing the stored information back into a light pulse, which then traveled on as if nothing had happened. Okay, so just like the truck, it stopped altogether, and then the truck continued moving. Okay, so here's light coming into a prism, right? Here's a prism. Okay, here comes light. Okay, hits it. It goes slowly. And if you want, stop it altogether. But then the question is, when it comes out, does it pick up speed again? And if so, what compelled it to pick up speed? Why does it travel again at 300,000 kilometers per second? I mean, we can understand a car, okay, more or less. Car travels at 60 miles per hour, hits the water, right? But its wheels, everything is still rolling at 60 miles per hour, right? The only problem is being stopped by the water. But now you remove the water. In other words, it goes into the medium of air again, and it goes back to 60 miles per hour, because that's the speed at which the wheels were traveling or rotating or whatever, right? We can more or less understand it there. But how about the truck? The truck stops altogether. How do you restart it? And these people say they stop light. And then the next second, they just melted these atoms, they got them moving again, and light again traveled at 300,000 kilometers per second. By what mechanism? How did it go from 0 to 300,000? That's what I want to know. Okay. And this has been confirmed here. Here we have Derek Muller. He's a guy who peddles the party line, and he's going to tell you first that how these waves are created, the waves that travel, because I guess it's done with waves, right? And he's going to tell it to you. There it is. Listen to him.
Electromagnetic waves are made by accelerating charges, like by wiggling them up and down. Then the changing electric and magnetic fields they create team up as light and head off on their own.
Okay, so he's saying that there's something called a charge that moves up and down, and that's what the wave is, the wave of light, right? So he sets that up, and then he goes in there and he's going to explain that if the wavelength shortens, right? Listen carefully here. If the wavelength shortens, right, but you keep the frequency the same, then you have slower light, okay? So listen to him again. Here it goes. Give me a second. Here it goes.
Higher frequency light, like blue light, will cause the charges to wiggle with greater amplitude. And because of this, the charges produce higher amplitude electromagnetic radiation, which shortens the wavelength proportionally more, making higher frequency light travel slower and bend more than lower frequency light.
So let's see if I understand him correctly. He's saying you have little c, right? Little c is equal to 300,000 kilometers per second. That's the speed of light in a vacuum, right? More or less in air also, okay? Okay, so you have that speed of light, right? And the question here you have the equation. This is what he's saying. He's saying that if little c is equal to 300,000 kilometers per second, and you have frequency and wavelength, a little f and the f there and lambda there, okay? If you lower the lambda, if you shrink the wavelength, right, and keep the frequency constant or raise it a little bit, I guess, then little c is going to travel at a different speed. Instead of going at 300,000 kilometers per second, it's going to go at 100 for example, in this case, right? And so the question is this possible? Can you slow light down? And if you can, then how do you speed it back up again? I mean, how do you raise the wavelength again? Okay, by what mechanism? And they never explain that. They just say, it is so. It has less things to bounce against, less atoms in the less dense medium. And you can't get anything less dense than, I guess, space, right? So that's where 300,000 kilometers per second. But see, if this is true, if you can fool around with a wavelength, right, and you can fool around with a frequency, why not raise both the frequency and the wavelength and travel faster than light? See how simple it was? You want to travel faster than light? Instantaneously? Hey, there you have it. Just raise the frequency to infinity and the wavelength to infinity. Why can't we do that? What physical impediment do we have? What stops us from doing something like that? And that's the question, you got to answer. These people avoid these important questions. Okay, so here we have, I'm going to try to explain, the couple of questions that we've got here. The first one is, why does light travel straight? Why is it directed? That's one issue. The other one is going through walls. Why does light go through walls? Okay. And another one is, again, this bending thingy and the speed of light. Those are important questions related to light. And we're going to try to answer all these questions now. Okay, so here we have a light bulb, okay? And you can see that just by looking at the picture, you can see that light is going in every direction. It's going radially. Okay? Light bulb doesn't direct the light in one direction. It goes in every direction simultaneously. Okay? And that's what I'm showing there. Now, what is our version of the atom? Okay, here's one atom, only just one atom, okay? And you can see our atom is made out of this electron shell, electron membrane, which is weaved by all these threads, the red one there, going around, and that encapsulates the proton star. So the atom was not what they told us all these 100 years now. Here you have a comparison between them. You have the, let me put it in motion here. Okay, so here you see our atom is just pumping back and forth. That's the quantum jump. And by doing so, it torques every rope that converges upon it. And all these ropes come from every single atom in existence in the universe. Okay, so let's get at least the notion of what we're proposing right. Okay, you don't have to agree. We're making an assumption here that an atom looks like that, like a ball of yarn encapsulating a star. One thread goes to the center of this ball, and the ball is made out of the other threads that go around. And those two threads, they come from the ropes, the electromagnetic rope, which is a pair of twined threads. One thread goes straight, and the other one curves around. That's it. That's our model. Okay, you don't have to believe in it. That's the one we're going to use to explain. Okay. On the other hand, you have the ridiculous planetary model that you see on the side there, on the right-hand side, which is the electron bead. That's what they think the electron is. And this electron bead jumps back and forth between energy levels. By doing so, it absorbs and releases energy, whatever energy is, right? Not a physical object, it's just a number, just a value that they calculated. And yeah, and that's what they're saying. And all these waves that you see there, the transverse wave, they come out. That's the energy that's flowing outwards when the atom falls, or they come in when the atom absorbs energy. That's it. Okay, that's the quantum jump version of quantum mechanics. Okay, and so the question is whether this in any way represents, what we have out there, what Mother Nature does. And here, we're going to put the bulb that we just showed, we're going to put it with a single atom, just one atom. Obviously, a bulb has gazillions of atoms. We're just going to put one just to illustrate the fact that light is coming out of there radially. Okay, so here it is. Okay, that's what we're saying. We're saying here we have the bulb, and we're assuming there's a single atom. We're just looking at one atom in the center, and that one has all the ropes converging upon it. It's vibrating, and all the ropes are being torqued. That's why light travels radially. That's the direction of light when it's not contained in any way, okay? So what we're going to do now, we're going to contain it just to show how we direct light. And here we have the same bulb, okay? And you can see we've chopped off, somehow blocked the light bulb from every angle except, given direction. The front side, it can go straight ahead. But you can see that a lot of the ropes are going sideways, and they crash against whatever black stuff that we use to contain the light. So they hit there and they die there. In other words, they don't go through on the other side of that black container. Okay, we'll call it a container. Okay, and only the ones that are going forward are the ones that are going to make it like a sharp pencil, a ray, a beam. Okay, and so just want you to understand that concept, that we're blocking the light from all sides. We're directing the light in one direction at this point, okay? Okay, so let's see where we go here. We need to show this before we move on, and that is that we're going to explain the spectrum of light. We're not going to explain it like they do in quantum mechanics. We're not going to use the wave, the transverse wave, the standing wave. No, we're going to use ropes. Okay, so we're going to replace the entire spectrum with ropes. Okay, so you can see there, if you want to see the violet has shorter lengths, right? Shorter lengths than the red. Red has longer lengths. Okay, so that's what they've been looking at all these years. According to us, we're saying that there's no such thing as a wave. You need to identify the object, and the object is a rope, and all we're talking about the different lengths of the lengths of a rope. That's it. And so when you have a torsion of these ropes, you have links which are shorter, and you have more links per unit length, and vice versa. When you have red ones, for example, there, the links are longer, and you have fewer links, meaning the frequency is lower. Okay, that's what essentially we're simply replacing the wave with a rope. Everything else remains the same. There's no difference otherwise, okay? Okay, so here we have a prism, okay? We're going to look at that first. Here we have a prism, and we see how light is broken down. It's broken up into pieces, okay? But we're going to replace this with what? Well, with what we just showed, with the links of ropes. We're going to replace them with ropes. So what we have is ropes torquing inside the prism, and when they come out, we still have ropes, okay? And one of the questions we need to ask or answer, I guess, is why do we have those different color ropes, and why are they coming out also with different colors? And has the speed changed, okay? I think we're already more or less answering that light does go through walls, okay? Because you have a wall there of a prism. It is a wall. It's a solid wall, right? And it's going right through there, okay? So keep that in mind. Okay, so one thing that you have to keep in mind is that all this can fool you, because you're seeing the light, from a distance. You're from a bird's eye perspective, right? So you're seeing the light go in. You're going through the prism. You see all of this, right? And you see the light coming out. Okay, you see all that. But what are you seeing? Are you seeing what Mother Nature does? Are we confusing the observer with what's actually happening with light going through the prism? Okay, we need to distinguish those two. And so this is the observer's version here, okay? The observer is seeing light that is being reflected and refracted towards his or her eyes, okay? So light is being pumped by those atoms inside the prism, and it's redirected. Some of it is going straight and going to the other side, and some of it is being reflected or refracted, I'd say refracted in this case, right, towards your eyes. And also from the beam that comes out. I mean, you're not staring directly from the front of where the beam is coming into your eyes. No, the beam is going sideways, and it's stimulating air atoms, air molecules, right? And those are the ones that are arriving at your eyes. So you're looking at this whole thing from, you have a side view, Okay, you have this side view of this whole phenomenon. Keep that in mind, okay, because it gets complicated after a while, when you're saying, what am I staring at? Well, you're seeing light coming to your eyes. Say, okay, the light went that way. Yeah, the light may have gone that way, but what you get is the observer's version, which is light being refracted towards your eyes from the atoms that are being stimulated as the beam goes horizontal to your field of view, okay? Okay, so here we rub it in by showing what happens with a lens. Lens, you can think of it as two prisms, one against the other, okay? So here you have a lens, and you can see the pattern that develops when you shine a white light from the top, right? You have this concave version, and it goes downwards. And the white light that goes from the bottom, because it has this convex, it's concave, but in the opposite direction, it forms this red point farther away, and the blue is closer by. And that's going to be very important, because remember, blue has shorter wavelength, right? Shorter links, and red has longer ones. And you can see there now part of the answer of why we see this, okay? Because what you're seeing there is exactly that the blue will have shorter wavelength and the red will have longer wavelength, okay? So that's one issue. The other thing you should keep in mind, that if little c is equal to frequency times wavelength, if the wavelength changes, like it's longer or shorter, frequency will change in the opposite direction. They're inversely proportional. Okay, so here's a laser pointer. Yes, all of you have seen one, right? There's a laser pointer. And we're going to put some atoms in there, but we're going to put our atom. We're going to put the rope atom, rope model of the atom. Okay, we're going to put several of them in there. Okay, so here you see them pumping. Okay, but what happens with the atoms that are inside the tunnel, we'll call it, the body of the laser pointer? Well, whatever light comes out of there from the sides, right, just gets chopped off by the enclosure. The only ones that will be allowed to go, right, to move, are those that go towards the right, in this case, in a straight line almost. So you're redirecting light in a given direction. You're sending light in a given direction, whatever sending means here, okay? So I just want you to see how light is not going, the light from the sides, you're not going to see it. Even though light does go to the sides and even goes past the enclosure, we're going to find out why you can't see the light that doesn't come through walls in a minute. But right now we're allowing only the light that goes towards the right through a little, pencil beam, ray, whatever you want to call it, typical of a laser pointer, okay? And so here's light coming out of there, okay? We're going to annihilate all the ropes that are coming towards the sides. There are ropes going through there, because every atom in the universe is connected to all others, according to our proposal, our hypothesis, right? And so all atoms are interconnected. That means there are ropes extending from those atoms to your eye, even though they go right through the enclosure. But the light that is being stimulated, right, by these atoms, that one can only go through the opening that you have there. And that's how we direct light in a given, send it in a given direction, so to speak. Okay, so I hope you understand that part. Okay. But I just wanted to set that in there. In other words, if you have a laser pointer, right, and I'm going to use the light, not the because it's a very small pinpoint red light. I think it's 620 nanometers. Anyways, we have light, okay, and you can see the light, but you're saying, why doesn't light come from the sides? And yeah, whatever's creating light in there is going through the sides as well, but it's being blocked by the enclosure. And we take that for granted. We say, well, yeah, it stopped light. That means light went down to zero. Light stopped at the atom on the wall and doesn't move anymore. It just ended there and that's it. And no, according to the rope model, the ropes extend outside here. They extend right out of there, right? And go to other atoms, including right now two atoms in my eye. Okay? And so I can't see the light, and the question is why? Why doesn't the light, the visible light, go through the walls, right? It only goes in that direction. Yeah, okay. So the only light I can get to see is the one that comes out of the front end, because that's not blocked. What's blocked is from the side. So we're directing light, in other words, right? Okay, now the question is, light can go through walls. Can objects go through walls? And people say, well, no, objects cannot go through walls. And that's a lie. That's a total lie. And I'll prove it to you today. You heard about Superman, right? Well, there was a show, Superman, in the 60s, 50s and 60s, with George Reeves, who I guess committed suicide. He was on the news lately. Anyways, and he showed that, he could see through walls, which was a weird way of doing light, because light was not coming from whatever he was seeing. Light was coming out of his eyes. It was X-ray vision. So the light was going out of his eyes through the walls to see, Lois Lane taking a bath or whatever, that kind of thing. On the other hand, if he wanted to go through walls, he's the man of steel. He'd just break through there, right? That's the notion we have. Today I'm going to show him in exactly reverse. He's trying to use his X-ray vision. He can't see through the wall because it's a guy who built this prison, right? He's in there, and Superman's got to get him out, take him to court. If 7 years are up, well, the statute of limitations runs out on him. So he wants to get inside that room and get this guy out, right? He wants to talk to this guy or whatever. And the point is, he wants to go in, but he's not going to break in, like break the whole place up, because he apparently can't break it. But he does something else. He blends, he flows through the wall, okay? But at the same time, he can't see through that same wall. And here it is. So it's the other way around. His X-ray vision is no good here. And here's the visual part. Okay, listen to this. And I like it because one of the mugs there, he says, I think you need glasses. You need glasses, or maybe you're getting too old. Listen to him.
Glasses, Superman. Oh, you're slipping, old boy.
So Superman needs glasses. Forget about X-ray vision. But this is how he goes through a wall. He's a body now, okay? We're not talking about vision here. We're talking about the body, okay? And so let's see if this is true, okay?
Of him. He's coming after you, Paul. He melted in the wall as if it soaked him up. If he shows up in there, tell him we've got Lois Lane and Jimmy Olsen.
Hey, wouldn't it be funny if he got stuck in the wall and never could get out?
See how easy it is? You just put yourself close to the wall and just try to seep through it, That's the way it's done. Anyways, if you want to try it one day and tell me how you did, if it was successful. Anyways, waves, can they go through walls? Okay, and here we have a candle, right, in the dark somewhere, and the light's going to go through that wall and reach the guy's eyes. Is that possible? Does light go through walls, or does it stop at the wall? Well, what's happening there, right? And here's proof, evidence, okay, one piece of proof evidence. People like proofs. It's known as the Wallabat, and it's used by electricians and so on. so that they can locate wires on the other side of a wall. And it's done through light, right? Different versions of light. It's an X-ray thing. It can go right through the wall and detect if there's a wire or a cable or a pipe, so that when they drill, they don't break it. Okay, so yeah, at least X-ray goes through walls. And what is X-ray? It's light. It's just a different form of light. It's an invisible light for us, right? For our regular eyes. So there's the first proof that, yeah, light does go through whatever light is, right? I mean, it goes through the walls. Okay, it can go through walls. And here's the rope going through walls. Again, you can see it there with the little candle. And you have an atom that's pumping right at the tip of the candle. And it's pumping right through the wall. But why can't you see it? Why can't that fellow there, why can't he see that light? Why can't he see the candle? Well, I've had a talk with my son Adrian. We have two different theories for this. So, you might come up with even a third one or a fourth. And that is, in my version, the atoms from the wall are pumping also towards his eyes. And there's a lot more of them. And closer to him, that's one issue. But all of them are pumping at a slower rate, or at a different rate than the candle, right? So you have, a lower frequency and higher wave length. That's why the guy can see the wall, but he cannot see the candle behind it. Now, that atom that's pumping there, it's connected directly to his eye, right through the wall. The rope goes right through the wall. But it goes through the atoms that are in the wall. It goes along. It's superimposed on all the other atoms that are in the wall, the ropes that are coming from the wall. So it's like you have a high frequency within the low frequencies, but the low frequencies by far, are eclipsing, you could say, the what's coming from the candle. My son has a different version. He says, according to him, he thinks what's happening here is that the atoms are somehow squeezing, the light out of the candle. In other words, those atoms are connected also to the atoms on the wall, and they're slowing down the frequency of the light coming from the candle, from the fire there. And so those are two versions. We're still fighting. And of course, I'm always right, so he's got to be wrong. Okay, so we're going to figure it out. Anyways, my version is you have, once again, right? We have every atom of the candle is connected to every atom in my eye. Okay. Every atom of the fire is connected to every atom of my eye, right through the wall. But why don't I see the candle? Well, because the atoms in the wall are, in other words, the ropes are going right through the other atoms that are connected to my eye. They are filled with ropes as well. And so we have the light from the candle going through all this coaxial of ropes that are also going through to my eyes. And so they're being suppressed, you could say. You could say they're being eclipsed. And so I'm not receiving the light from the candle, even though the atom there is connected to the atom in my eye. So yeah, even under the rope model or under a quantum model, light does go through walls. The question is, why can't we see through the walls, right? Like good old Superman to try to see through the wall. Okay, one thing that might help us explain it are the rainbows. They will probably help us explain at least the prism. Okay, here it goes. We have here these rainbows, and you always wonder why they're circular. Well, they're circular because they really go underneath the ground as well. If you had God's eyes and you could see through the earth, well, you would see the rainbow go all around. Okay, so it's a circular type pattern, and we only see half of a circle only because the ground is in the way. But what I want to show you here is that what is known as Alexander's band, and that's between the two rainbows. The one on top being, you can see the farther out is a little lighter. It's not, you can't see it as well. It's not as, it's fainter. It's not as visible as the other one. And what's happening here is you have this region between the two rainbows. The rainbow that's brighter and the rainbow that is darker, you can see there's a region. And here, let me show you what I'm talking about in a better picture. You can see between the rainbows, right? That region, and that region's called Alexander's band. Okay, and the question is, why does that form? What's happening there? Why are we seeing nothing there? Why aren't we seeing a rainbow there? And why are we seeing another rainbow farther out? So we need to kind of answer that question. What is happening there? Okay, so here's a first approximation to an answer to that question, and that is that it happens also with the slit experiment. Okay, when you do the slit experiment, we don't see it, right? But the fringes, each one of those fringes has a rainbow in it, and as you can see, the rainbow has, on one side they go in one direction, and then on the other side they go in the other direction. You saw how the lens showed that from the bottom shows differently than from the top, because the blue one is closer to, it has a shorter wavelength, and this is the same thing that you're seeing there. It's the angle, right? And by changing the angle, what you're seeing is, the rainbow changes direction. If it went from blue to red, now it goes from red to blue, right? And so it's important to note that during the slit experiment, you do get the rainbow, but you got to do it really, really good in order to get that rainbow. Not everybody can do that. You got to have the right equipment, etc. Okay, so here you see it again. Okay, why the rainbow? Why you see the blue on the inside and the red on the outside, and that's because the blue is the shorter wavelength, length in our case, right? What you see, the distance between the eye of the observer and the blue and the red, well, there's a difference in length. Okay, and what we're talking about, the length of the rope. So that essentially gives you the idea of why the rainbow and why also the prism, right? Because that is the explanation for both. Things that you must keep in mind, things that quantum mechanics cannot answer with its wave, right? And with its particle, and it's the speed of light, why it's a constant. And we can with a rope. There we see why, and I always show this. The links, if you have many links, if you tighten this up, you get many links. You have more links, and length is shorter. But as the links get longer for the same amount of rope, you get fewer links. And that's what the equation C equals frequency times wavelength represents. You can't do that with a wave or with a particle. You cannot explain that at all. In other words, you cannot explain the constancy of the speed of light. And that's why they have to shorten, they say, well, we shortened the wavelength and now light travels slower. Yeah, and they even brought it to a full stop. Yeah, show me that. Okay, that's their interpretation. It doesn't mean that they really slowed light down from 300,000 kilometers per second to 100,000 kilometers per second. But that's the idea these people have, because they're talking about particles, photons, right, hitting atoms, being absorbed and re-emitted. And they say, well, if you have a lot of atoms and it's doing that a lot of times, and that slows light down. But then the question again is, when it goes back to the normal medium, why does light pick up speed again and go back to 300,000 kilometers per second? So that's one thing that the rope model answers, which the wave or particle hypothesis cannot answer. Here's another one. It's called ray reversibility, and you never hear mathematicians talk about it at all. But ray reversibility also debunks. I hate to use the word debunk because that's an opinion. It just shows that you cannot really explain a phenomenon such as ray reversibility with either the wave or the particle nature. And here you'll see it, okay? Ray reversibility means that light retraces its exact path. Okay, its exact path. Now with ropes, you can explain this because the rope would follow this whole thing, right? In other words, the atoms are connected from atom to atom. If you move the atoms any way you want to, it doesn't matter. The torsions along the rope that is there already will be always the same. You can move that around, doesn't matter. But see, how do you do it with particles? Particles, if you move this whole thing, especially at the speed of light, well, the particle would not hit the flashlight again. Okay, the flashlight would send it in, right? It bounces. When by the time it comes back, everything already moved in the universe. In fact, you cannot explain with particles. Imagine just the sun twirling around. It spins, and not only does it spin, but every atom of the sun spins and does different things. Imagine now light from the sun sending, straight ahead, all the photons in a straight line, right? Well, as soon as the sun spins, the same atom and the next, they're going to send, the next photon to the side, and then the next one to the side. It would be like a sprinkler system, when you send water around, it would sprinkle in every direction. Light would be always curved. You would never see straight. And that's the problem also with both the wave and the particle. How do you explain it with waves? I mean, a transverse wave, are you bending the wave every time the sun turns around? It just bends or curves the wave? Is it a banana? Is that what the wave is? And then the other thing similar to that is this one, which is the laser ranging experiment that they ran. Well, the only way you can really explain this is if every atom on the moon is physically connected to every atom on Earth. The Earth swings the moon around like, you would swing a ball around the top of your head. And so what happens? The laser pointer, which is connected by electromagnetic ropes to the lunar ranging mirror they've got over there, right? So light can come and go along those ropes, and the moon can go anywhere it wants. Light's not going to get lost because it has a fixed mechanism along which it torques. But how do you explain this with particles? I mean, you sent particles and the moon moved. And then you're supposed to get the rebound, the reflection back to you. That's one problem. The other problem, which I think is a more fundamental problem, when these guys focus their laser at the laser ranging at the mirror on the moon, they already have a problem. Because if light takes a second and a half approximately to reach the moon before it comes back to us, it's 2.5, something like that, seconds round trip, because it's 300,000 kilometers per second and the moon is like 380. So it takes a little more than a second to go. That means that before you send the laser out, you already have to point to where the moon is going to be 1 second later. You don't point it directly at the mirror. You have to point it further out. And the moon travels 1 kilometer per second around the Earth. So in 1 second, it's 1 kilometer away. So where are you going to point your laser pointer? You can't point it at the laser where the laser is now, because the laser, the mirror, is going to be 1 second later, 1 kilometer away. So you have to point it where the mirror ain't. You got to point it 1 kilometer to where the mirror is going to be in 1 second. So again, a bunch of nonsense to use both particles and waves. The only way you can explain it if there's an attachment, an elongated object rope, right, that interconnects an atom on the moon, anywhere on the moon, the mirror included, to every atom on Earth. Then yes, you can send signals through that rope, in this case, right? And the moon can move anywhere it wants. The signal's always going to go along the rope in a straight line because the rope is taut.